The Art of Algorithmic Mastery, unlocking efficiency through strategic design in an era where computational power is both abundant and essential. Understanding how algorithms function at their core remains vital for developers, data scientists, and engineers alike. Algorithms are the building blocks that determine not only what our software can do but also how efficiently it accomplishes its tasks. Mastering algorithm design requires more than memorizing common patterns. It demands a deep comprehension of trade-offs between time complexity, space complexity, and practical performance considerations. This guide explores advanced optimization strategies that elevate your algorithmic skills from competent to exceptional. Foundations of efficient algorithm development. At the heart of every efficient algorithm lies a clear problem definition. Before diving into implementation, spend significant time analyzing requirements and constraints. A well-defined problem statement serves as the foundation upon which optimal solutions are built. Misunderstanding input size limitations or ignoring edge cases often leads to suboptimal implementations. Consider scenarios where inputs might be empty arrays, duplicate values, or extreme numerical ranges before writing any code. Time complexity analysis using Big O notation provides crucial insights into how an algorithm's runtime scales with increasing input sizes. While theoretical bounds help compare approaches, real-world performance may differ due to hardware specifics and constant factors. Space complexity assessments ensure you're not sacrificing memory efficiency for speed gains unnecessarily. Balancing these two aspects creates robust solutions suitable for various deployment environments. Optimization tip: always measure actual execution times alongside theoretical complexity analyses. Real-world benchmarks provide invaluable context for making informed decisions about implementation choices. Remember, the most theoretically optimal solution isn't always the best choice when considering practical application requirements and system constraints. Advanced data structure utilization techniques. Selecting appropriate data structures significantly impacts algorithm performance. Hash tables excel at lookup operations while linked lists offer flexibility for dynamic storage needs. Choosing wisely ensures optimal access patterns and minimizes unnecessary computations. Understanding amortized time complexities helps predict average case behavior rather than focusing solely on worst-case scenarios. This knowledge becomes particularly useful when implementing complex data structure operations. For instance, using a balanced binary search tree instead of a simple array can drastically reduce search times in sorted collections. Similarly, choosing between different queue implementations affects overall system throughput depending on use case requirements. Profiling tools enable precise measurement of data structure overheads during development cycles. These measurements inform better architectural decisions regarding which structures will yield the highest performance benefits. Data structure performance benchmarks. Recent benchmark studies comparing standard library implementations show hash maps outperforming binary trees by up to 3x for insertion/deletion operations under typical workloads. However, binary trees maintain superior ordering properties that prove advantageous in certain specialized applications. Cache locality optimizations become critical when dealing with large datasets stored in memory. Contiguous memory allocations provided by arrays often lead to faster processing compared to scattered pointers found in linked list structures. Modern processors employ sophisticated caching mechanisms that favor sequential memory accesses over random ones. This characteristic makes arrays particularly effective for high-performance computing scenarios requiring massive parallelism capabilities. When working with graph representations, adjacency matrices offer O(1) query times but consume excessive memory for sparse graphs. Adjacency lists strike a balance between accessibility and memory consumption for most practical implementations. Divide and conquer paradigm refinements. The divide and conquer approach breaks problems into smaller, manageable subproblems whose solutions combine to form the final result. Classic examples include merge sort, quicksort, and binary search implementations across various domains. Careful selection of pivot elements in partitioning schemes dramatically influences algorithm performance. In sorting algorithms, median of medians techniques provide guaranteed linear time complexity at the cost of increased constants involved in computation steps. Recurrence relations model the asymptotic behavior of recursive algorithms. Master theorem simplifies solving these equations without needing full mathematical derivations each time. Awareness of recursion depth limits prevents stack overflow issues in deeply nested calls. Tail call optimization features in some languages mitigate these concerns effectively. Practical application: implementing fast Fourier transform (FFT) algorithms demonstrates the effectiveness of divide-and-conquer principles applied recursively to achieve near-linear time complexity improvements over naive approaches. Dynamic programming optimizations: dynamic programming solves overlapping subproblems optimally by storing intermediate results through memoization techniques. This avoids redundant calculations inherent in naive recursive solutions. Identifying optimal substructure properties is crucial before applying DP techniques. Problems exhibiting such characteristics typically benefit greatly from structured approach. State representation defines the dimensionality of the DP table used to store computed values. Carefully chosen states minimize memory usage while maintaining necessary information for future computations. Bottom-up versus top-down approaches present distinct advantages depending on specific requirements. Bottom-up methods avoid recursion overheads while top-down variants facilitate easier debugging processes. Note: for large-scale problems, space-efficient variations like rolling arrays can drastically reduce memory footprints without compromising correctness guarantees. Real-world example: shortest path finding algorithms like Dijkstra's utilize priority queues combined with dynamic programming concepts to efficiently compute minimum distances in weighted graphs. Greedy algorithms: when simplicity surpasses complexity, greedy algorithms make locally optimal choices at each decision step, hoping they lead to globally optimal solutions. While not always correct, they frequently provide excellent approximations with much lower time complexities. Huffman coding exemplifies successful greedy strategy application in lossless compression technologies. By selecting lowest frequency characters, Kruskal's and Prim's algorithms demonstrate how greedy principles construct minimal spanning trees efficiently through careful edge selection heuristics. Proving correctness for greedy approaches usually involves showing that making locally optimal choices never precludes reaching global optimums, a challenging yet rewarding analytical exercise. Caution: greedy methods fail spectacularly for problems lacking optimal substructure property or requiring consideration of non-local effects in decision-making processes. Backtracking search enhancements: backtracking algorithms explore potential solutions incrementally, abandoning paths that violate constraints early. Pruning techniques significantly enhance performance by eliminating unpromising branches promptly. Constraint propagation reduces the search space by deducing implications of current assignments automatically. This technique proves especially powerful in combinatorial optimization problems. Heuristic orderings influence backtracking efficiency substantially. Choosing variables based on domain reduction rates improves chances of finding valid solutions sooner rather than later. Forward checking extends basic constraint propagation by monitoring remaining value counts across unassigned variables, enabling earlier detection of inevitable failures. Performance insight: incorporating intelligent pruning strategies can reduce search spaces exponentially, transforming intractable problems into solvable ones within reasonable time frames. Tip: visualizing the search tree structure helps identify areas prone to frequent backtracking, guiding further optimization efforts toward those regions specifically. Randomized algorithms: embracing uncertainty for speed gains. Randomized algorithms introduce probabilistic components to achieve expected polynomial runtimes for otherwise exponential time deterministic counterparts. These methods rely on statistical assurances rather than absolute guarantees. Monte Carlo algorithms accept small error probabilities in exchange for substantial speed increases. Las Vegas algorithms guarantee correct outputs but have variable runtime durations dependent on random choices made during execution. Rabenkarp string searching utilizes hashing with randomized probing to detect pattern matches efficiently despite occasional false positives resulting from hash collisions. Bloom filters represent another prime example where randomness enables highly space-efficient membership testing with controlled probability of false positives. Important note: understanding failure probabilities is essential when designing systems relying on randomized algorithms, ensuring acceptable reliability levels are maintained through proper parameter tuning. Evaluating algorithmic trade-offs in practice. Choosing between competing algorithms requires evaluating concrete metrics beyond theoretical complexity measures. Actual runtime comparisons reveal how different implementations perform given specific hardware configurations. Microbenchmarking isolates individual components, allowing focused evaluation of particular optimizations' impact on overall performance profiles. Tools like Google Benchmark facilitate accurate timing measurements across diverse platforms. Memory profiling identifies hidden inefficiencies related to object creation, garbage collection pauses, or cache utilization patterns affecting execution speeds indirectly. Load testing simulates realistic workloads, helping uncover bottlenecks that emerge under concurrent user scenarios or large-scale data volumes. Actionable strategy: maintain version control history. Tracking performance changes over time allows regression analysis, identifying when modifications introduced unexpected degradation in key metrics. Emerging trends in algorithm research. Quantum computing promises revolutionary advances in algorithm design through quantum supremacy demonstrations. Shor's algorithm showcases how quantum mechanics enables factoring large numbers exponentially faster than classical alternatives. Machine learning integration opens new frontiers in adaptive algorithm design. Reinforcement learning agents autonomously discover novel optimization strategies through iterative trial-and-error processes. Federated learning introduces privacy-preserving distributed computing models where sensitive data remains localized while still benefiting from collective intelligence improvements. Neural architecture search automates discovery of optimal neural network structures by treating hyperparameter configuration as an optimization problem itself. Future outlook: as technology continues evolving rapidly, staying abreast of emerging research directions ensures continued relevance and competitiveness in algorithmic innovation spaces. Conclusion: this exploration has highlighted numerous strategies for optimizing algorithms ranging from foundational principles to cutting-edge developments shaping tomorrow's computing landscape. To truly master algorithm design, continuous practice combined with rigorous analytical thinking forms the cornerstone of professional growth. Stay curious, experiment relentlessly, and remain open-minded about exploring unconventional approaches when faced with challenging problems.